What is up, good people? First video of the year. I'm very excited. We are in the review chapter, section 1. That's why it's R.1, the real number system. But before actually we get into that, I wanted to explain a couple things. First of all, you are watching a video, obviously, and if you have any questions, you're not going to be able to ask me directly. So, I mean, you could email me. A lot of people do, or you could text your friends, or you could Google the answer, or whatever. But if for whatever reason those seem unsatisfying or not desirable, then go ahead and write down your questions. In fact, if you're not thinking about what I'm saying and about what I'm asking you to write down, then you're probably not coming up with questions. So I want you to think. I want you to somehow wrestle with. And if you have questions, I want you to write them here. You're required to bring questions to class. You need to fill that out. So, as I talk, think about things you might want to ask me in class or ask your group mates. Write them down there. Also, at the last school that I was at, I had a group of students, and this is not you guys are awesome, but I did have a group of students who were just watching the video and not listening to it. And I just think that you need both. You need to be able to see and listen to what I'm saying and take the two combined together. So just to make sure that everyone's listening, I'm going to drop some personal information and about myself, and I want you, when you hear it, I'm going to ask you to write it down there, and I'm going to check to make sure you heard it and you're hearing everything. So you can write down the audio check information right there. All right, the real number system. So what I want to do is explain this chart, the real numbers, and this is how all real numbers are organized. And when we say real numbers, we actually mean all the numbers that you know of, really, or all the numbers that we interact with on a number line. Now, there are imaginary numbers and there are complex numbers, but we're not going to talk about those just yet. We're just talking about the real numbers, all the ones that you normally experience in day-to-day life. So, they're organized very much the same way you could say that the cities in North America are organized. We've got some cities in the United States, and these are awesome. We've got like Philadelphia, New York City, Cheltenham Township. These are all cities in the United States. Then we have other cities that are not in the U.S., and that's fine. We've got like Quebec, Montreal, Mexico City. In fact, I lived in Guatemala City for the past 3 years. I want you to write that down as part of your audio check. How long was I? I'll give you the first one. I want you to write down Guatemala City. Bergman lived in Guatemala City for 3 years. Audio check. So, there are cities in the U.S. and cities not in the U.S., and that's fine. Within the cities of the U.S., there are cities like New York, L.A., Seattle, Chicago, and then there's also Philadelphia, Harrisburg, State College, Pittsburgh. Some of those cities are cities in Pennsylvania. It's a smaller category. And all the cities that are in Pennsylvania are also part of the group cities in the United States, and they're also part of the group cities in North America. And then we have even one category further, the cities in Montgomery County. I believe these are all true, although I don't know, I haven't lived here all that long. So I believe these are all cities in Montgomery County. They're also, if a city is in Montgomery County, it's also in Pennsylvania, it's also in the United States, it's also in North America. So these are categories within categories. That's exactly how we're going to think about the real numbers. So you can see here, all real numbers can get divided up into two categories. Those that are rational and those that are not. So rational numbers, and this is the hardest distinction, I think, trying to figure out what's rational and what's not. So rational numbers are all the numbers that can be made into a fraction. They have decimals that either terminate or they repeat. So, and then irrational is the ones that cannot be made into a fraction. The decimals do not terminate and do not repeat. So you can see here some rational numbers would be, the number 0, the number 5, and then the number -5, and even -8.3. This decimal stops. It terminates. This decimal repeats. The pattern is 181818. In fact, if you wanted to, I could even turn it into a fraction. It's 18 over 99. Ask a calculator. Just take 18 divided by 99, you'll get a repeating decimal, 18181818. Then, of course, these are fractions. They can be made into fractions. All of these can be made into fractions. Even this, negative 83 over 10, can be made into a fraction. Let me show you something that cannot be made into a fraction. Oh, even these numbers, this can be made into a fraction, 5 over 1. All these numbers can be made into fractions, but these cannot. You take the square root of 3, you get a really long decimal that never repeats. Square root of 10, same thing. Pi, 3.141592653, it just keeps on going, and it doesn't stop, and it never repeats. These cannot be made into fractions. Now, here's another one. Let me show you this number. It's a well-defined number. 1 0, 2 zeros, 3 zeros, 4 zeros. 1, 2, 3, 4, and then you put a 3. This is a number that is well-defined. It has a specific location on the number line. We know exactly what it is and what the decimals are, and although there is a pattern, it's not a repeating pattern. The blocks keep changing every time, and for that reason, this is not able to be made into a fraction, it's not a repeating decimal, and it's not a rational number. Within the rational numbers, you've got other ones, a smaller category called the integers, and you can express the integers like this, in what's called roster notation. You're basically listing out all the numbers that are in the set. The set of all integers are all these numbers. There's no decimals at all. So within the integers, you've got positive integers, negative integers, and you've got the number 0. So within the integers, the numbers 0, 1, 2, 3, 4, 5, and continuing are whole numbers, and even within the whole numbers, you've got natural numbers. So a natural number, I want to be very clear, is both a natural number, a whole number, an integer, a rational, and even a real number. The number 1 is a real number. It's also a rational number, it's also an integer, it's also a whole number, it's also a natural number. So, when we take a look at different examples, there's lots of categories that they can belong to. 19 is a natural number, therefore it's also a whole and an integer, rational and a real. 3/4 is not natural, and it's not whole. It's not an integer, but it is a rational number. It can be made into a fraction, and therefore it's also real. -6 is not a natural number, it's not a whole number, but it is an integer, therefore it's also a rational and a real. 0, you can see here, 0 is a whole number, but it's not a natural number. Because it's a whole number, it's also all the smaller categories. The cube root of 19, wow. Okay, so the number that when you multiply itself 3 times, you get 19. Well, there's no easy number that does that. It's like a really complicated, never-ending, never-repeating decimal. So is it rational? No, it's not a rational number. It's irrational. Therefore, it's not an integer, it's not a whole number, it's not a natural number. But it is a real number. I want you to do -8/7, and I'll ask you about it at the end of the video. So pause it right now to check and X off -8/7. I will say that the square root of 7 is not natural, not whole, not an integer, but it's not even a rational number, but it is a real number. Okay, so we've got a new kind of notation to learn about. I'm sorry the picture is not better quality, but you can see here, that the graphs have these brackets and these bars on them. Okay, so bounded intervals and unbounded intervals. If you want to talk about all these numbers, the numbers that are in between -4 and 5, not including -4 and -5, what you could do is you could draw a graph, and it would look like this. You get -4 over here, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6. So what you can do is you can say, I want to talk about just all these numbers in between -4 and -5. Well, are we including -4 and -5? No. So because of that, we're going to put a little curved, almost like a parentheses here. This symbol right here means the set, the collection of all the values of x such that, and this means such that x satisfies this condition. And here's the condition, that x is in between -4 and +5, that -4 is less than x, which is less than 5. So there it is. Interval notation looks like this. Now this is a lot of handwriting, both of them, either the graph or the brackets, but if you want interval notation, then we can say, we just write the lower bound and the upper bound, separate them by a comma, and put parentheses on them. Parentheses because they actually do not include -4 and +5. Let me show you what it would look like if you did include the bound. This is the set of all x such that, by the way, I don't know if I mentioned this in class, but I did want to say that if I write something down, I want you to write something down. Everything you see, please write down on your notes. Set of all x such that x is greater than or equal to 1.7. Okay, so if you were going to graph this on a number line, you'd have 1.7, and x would be greater than 1.7. Now, before we used the parentheses, but here we're going to use brackets because we want to include 1.7. We want to show the people who are reading that, yeah, we're talking about all those numbers that are above it, but we're also talking about the number 1.7 as well. And the way that you indicate that in interval notation is you have a bracket, you say 1.7, and you go up to what number? Well, you go all the way up to infinity. That's like a sideways 8. And you can never reach infinity, so that's why we have the parentheses. 1.7, bracket 1.7, comma, infinity. I wanted to quickly mention, we've got some laws here, some properties that apply to it. Some of them apply to addition, subtraction, multiplication, and division. So the first law, the first property is the commutative property. And it's true in addition because the order of the numbers doesn't matter. You could have 3 plus 4, and that's equal to 4 plus 3. The order doesn't matter. The same thing is true in multiplication. 3 times 4 is the same thing as 4 times 3. However, the commutative law does not hold in subtraction. It does in addition, it does in multiplication, but 3 minus 4 is not the same thing as 4 minus 3. Similarly, 4 divided by 2 is not going to be the same thing as 2 divided by 4. So there is no commutative property of division. There is a commutative property of multiplication and addition. Associative property, the order of operation doesn't matter. If you have multiple additions, it doesn't matter which one you do first, because 4 plus 3 is 7, plus 2 is 9, and then 3 plus 2 is 5, plus 4 is also 9. So yeah, you could say that addition is associative. However, if you try and do that with subtraction, you have multiple subtractions, it really does matter which one you do first, because 4 minus 3 is 1, minus 2 is negative 1, and that's just not going to be equal to 3 minus 2, which is 1, and then 4 minus 1, which is 3. So subtraction is not associative. There is, however, an associative property of multiplication, because it doesn't matter what order you do all the multiplications, you're still going to get 24. So yes. division is not associative, because the order in which you do divisions does matter. Identity. An identity is a number that produces no change, and it's different for each of the properties. You have to make sure you know which property you're talking about. So for example, 0 produces no change. 5 plus 0 is still 5. So 0 is the additive property, the additive identity. Subtraction, 0 is still the additive identity because it produces no change. In multiplication, it's no longer 0, it's 1. 1 is the multiplicative identity. 5 times 1 is still 5. The same thing for division. Inverses are pairs of numbers that produce the identity. So here, 0 was the identity, and now 8 and negative 8, when you add them together, that produces the identity, which is 0. We call additive inverses opposites. 8 and negative 8 are opposites. I'm going to skip over to multiplication and just say that 1 is the identity, so 8 times 1 over 8 will produce the identity, 1. So 8 and 1 over 8 are multiplicative inverses. We call those reciprocals. And the distributive property. The only tricky thing I want to remind you about the distributive property is make sure you multiply both terms. 3 times 1, 3 times 9. There's students that often forget to do both. They just do A times B. But really you need to do A times B and A times C. This is what it looks like in general. Absolute value, just wanted to go over that real quick. So the absolute value of any number is the positive version. So if you had negative 3, the positive version of that would just be 3. 3 plus 2 is 5, so you would have the absolute value of 5. And the positive version of that would be 5. So if it's negative, make it positive. One application where that comes up handy is finding the distance between two numbers on a number line. So you've got a number line and you've got negative 2, negative 1, 0, 1, 2, 3. You want to know what is the distance between negative 2 and 3? Well, one way to do that is to subtract. 3 minus negative 2. The order in which you write these doesn't matter, because it actually doesn't matter if you go from 3 to negative 2 or negative 2 to positive 3. It doesn't matter if you go in this way or this way. The distance should be the same, and that's where the absolute value comes in handy. So 3 minus negative 2, change those to positive, not because of its absolute value, because a minus and negative becomes positive. And so that becomes the absolute value of 5, which is 5. So the distance between those 2 points is 5 units. Alright, good people, what I'd like you to do right now is I want you to finish watching the video, finish answering the questions, and then start, after you finish all that, I want you to start on assignment RA. What is RA? Well, this is chapter R, and A is the first assignment. I want you to get out your composition books and write down the problems lists and do at least the first problem. That way, when you get into class, we'll all just be ready to go and we'll have lots of questions that can get answered. Alright, so finish watching this video, answer the Edpuzzle questions, and then do at least the first problem in your assignment. Thanks, I'll see you in class.